my data, it is 00004 because this is the 0th byte, first byte, second byte, third byte, and fourth byte. Now here address in binary. Now this is my address where my data is stored. Now I am writing the same in binary. This is what is 4. Say rest all is 0. This is 0 and 0. This is 0, 4 zeros again. For this 0, 4 zeros again. For this 0, 4 zeros again. And last 4 is 0, 1 0 0. Now assume I need to shift this memory word by 2 bits upward the memory. Now I'm assuming k is equal to 2. That is, I want to shift the data by 2 bits in memory upward, and carry is initially initialized to 0. Hope you understood with this. Now here, now since I'm doing a 2-bit shift, if I go to the program, you can observe here x is left shifted by 2 bits. Now k value is 2 bit. Now I'll go here. Logical shift left by 2 bits, that is k is equal to 2 on the address. Now on this address which is written in binary, if I perform 2-bit left shift, what will happen? So these 2 bits will go out of the registers, and everything is body shifted, and this 0 1 comes here, and 2 more zeros will be added here. That is what this result you are seeing. After performing 2-bit left shift, this is what I am getting. Now 0 0 0 0 1. This 0 1 which was here gets shifted here, and these 2 zeros are introduced. Now what we are doing here, after getting this, I'm ORing with C. C initially initialized to 0. I have written 0 here. Now this 0 is nothing but I have written it in 32 bits. Now this C carry and this address after shifting left by 2 bits is ORed. This is ORed with this, and what I got is 0. Now in decimal it is 0 0. This is 0 0. This is 0 0. I got 0. Next, so this data which was here, now where it gets shifted? It gets shifted to the address 0. Now it was here earlier, now it got shifted here. That is the program basically. This is the C program, and I've tried explaining that program by taking a simple example here. Now, so this program you understood now, the C program and how it operates and how it shifts, you understood here with this example. Now improving the efficiency of the loop by unrolling. Now this, I want to improve the efficiency of this program. Now the technique what I'm using is the loop unrolling technique, and now I'm assuming in this example I took only one word as example, but this example is dealing with the 8 words. Now as I said, now I need to use the registers. What I'm doing here is I'm storing, since this program is not making a call to any of the thumb code, R12 is not there, or only if I save from R4 to R11 is sufficient, because only if I'm calling the function which is there in the thumb code or calling the function which is there in the ARM code from the thumb code, then 8-byte memory alignment is necessary. Now 8-byte memory alignment is not necessary for me. Now R4 to R11, if I save it onto the stack along with the link register, that is fine for me. And then this is reverse subtract operation which I'm doing. So 32 minus k, and that goes to kr, and these are all the alternative names which are used for the registers. We'll come to that later. In the next slide I'll show you. Now carry, as usual, it is initialized to 0. Then load multiple increment after. Now what I'm doing, from the stack, from this memory location I'm loading all this register x0 to x7. 8 words I'm loading simultaneously from x0 to x7. That is the range. Again, this x0 is an alternative name to some register, and x_7 is alternative name to some register. From this address I'm loading multiple data items from x0 to x7, and then finally ORing this, shifting the 8 words, so like this, and I got to do this for how many words? Now for 8 words. So this is for the first word, this is for this OR and move for the second word, this OR and move for the third, 4, 5, 6, 7 and 8. So totally it's doing for the 8 words. And then finally STIMA out y0. I'm just storing it back to the memory location. So new, this out is the new memory location. They get stored. Subtract 256 and then 250. The maximum is 2. 8 into 4 is 2. Sorry, 256 bits it is. 256. You have 8 words here. 8 word. Each word is 32. 32 into 8 it is. 32 into 8 is 256. If you have more than that also, say 512, then this loop is going to repeat for one more time. PNE, and finally carry, move it to the register R0 and restore back all the register from R4 to R12. Now in the previous example I just took one word, shifted from this position to this position, so it is a 32 bit. I just dealt with the 32 bit. So similarly you can deal it in multiples of 256. So 256 bits you can shift, 512 bits you can shift, 1024 bits you can shift, like this. This is the example. Now this code efficiency is more than compared to the efficiency of this program, because we have unrolled it for 8 times. That means simultaneously it is shifting 8 words in the memory upwards in the memory. Now register allocation is something like this. Now we were using out as the alternate name to the register 0, and similarly in is the alternate name for the register R1, N is the alternate name for R2, K is the alternate name for R3, and similarly here. See, X0 I was talking alternate name for R5, and similarly X7 R12, Y0 R4. See now, Y1 is again one more alternative for X0. What is X0? X0 is 5. There are the 2 alternatives for register 5 now. X0 is one alternative name, Y0 is also, Y1 is also another alternative name. Now I've used all the registers here. All registers are finished. There are 2 remaining variables, carry and KR. If you observe here, carry I have not assigned any register, and KR also I have not assigned any register. But only one remaining register is free, that is LR. I have only LR register remaining because LR I have not used, but there are 2 more variables to be allocated with the register, carry and KR. Now what to do with this? Now there are possible ways to deal when we run out of the registers. Here we ran out of the register because there is only one register available now. LR I can use, R13 and R15 I cannot use, but LR, R14 I can use. But still 2 variables, carry and KR. You can observe here, carry I have not assigned any register, and KR also I have not assigned any register. Now what I have to do when I run out of the register? Now reduce the number of register required by performing fewer operations in each loop. If you run out of the register, one option is you go for reducing the number of register by performing fewer number of operations inside the loop. Now in this loop we are trying to shift 8 memory words at a time. If you don't have the sufficient register, then you go for reducing. It's not possible for you to shift 8 words at a time because you don't have the registers available. You have already run out of the register. Then you can go for, instead of 8, you shift 7 words or 6 words. That is one possible way to deal with when you have run out of the register. Now in the previous example, that is what? In the previous example, we could load 4 words in each load multiple rather than 8. Now in this example we are doing 8 now. Now 8 have run out of the registers, so there are 2 variables yet to assign the registers, but I am left with only one register, that is LR. Now that time what I can do is I can go for dealing with 4 words instead of 8 words. Use the stack to store the least used values. Now in case if you run out of the register, you can go for using the stack. I don't have the registers available, then you can go for using the stack in order to store the least used data. More frequently used data you can hold it inside the register, and the least frequently used data can be always saved onto the stack. In the previous example, again, if I take that example, the loop counter n, for storing this, I can use the stack instead of the register because it is not more frequently used. It is used after shifting 8 bits. N I'm using, and right now n is the alternate name for the register R2. Now this register I can use. And the third possible way is you can alter the code implementation to free up more registers. Now just by doing some changes to the program, you can free many register. That is what you'll see in the next solution, next example I'll show you. Yeah, modified implementation. So modified implementation for this program now. Modified implementation here. Yeah, I'll show you. Yeah, modified implementation for this. The implementation is modified such that the registers are saved. Now to modify, observe this. We notice that the carry value need not stay in the same register. Now what we were doing in this example, we were storing the carry value in the same register, but this is not necessary. Now when we can start off with the carry value in y0 and then move it to y1 when x0 is no longer required, and so on. So like this, we don't have to store the carry in the same register. We need not designate a specific register for storing the carry. So the carry can be just shifted from one register to the another register. So this is what the simple technique, and we complete the routine by allocating kr to lr. So kr was remaining, and we understood now the carry. So carry and kr were remaining. Carry and kr were the two variables which were not assigned with any register. Now this is what the solution we have found. Now we have understood from the previous example that the carry value need not stay in the same register. Now carry value can be shifted from y0 to y1, and y1 to y2, y2 to y3, like this, without having a specific register designated for it. And now what we are doing is the LR, we are designating it to KR. Now this is what we are doing. See, the earlier in the previous example we were storing it into the separate register named carry. Now I'm using y0 itself. When it comes to the next example, it goes to y1. When it comes to the next word, it goes to y2. Like this it is carried, and finally we have KR register assigned for LR. So this is the code after implement. Yeah. Now using more than 14 local variables. I want to use more than 14 local variables. You understood 14 registers are can be used for holding the general purpose data. Now I want to create more than 14 local variables. Now you must store, if the variables exceed more than 14, so you have to use stack for storing the variables. So that is how this is the example. This shows that. See the nested loop. Now this is what we have to do. Whenever you call a function or a method, R4 to R11, you have to save it onto the R4 to R11, and the link register must be saved onto the stack. I'm saving them onto the stack. And now before starting this loop 1, see what I'm doing. I'm storing the loop 1 registers to the stack and set up the loop 2 here. That means all these registers you can use, because all these registers are saved onto this stack. And when I go to the loop 2, I store all the loop 2 registers onto the stack and set up the loop 3. And when I go to the loop 3, body of the loop 3, now here. I'm done with the body of the loop 3. Now I got to restore all my registers. This is how I'm doing in the reverse order. When you're popping, you got to do them in the reverse order. First I have saved onto the stack these registers, and next I have saved onto the stack all the registers which are used in the loop 1. Next I have saved onto the stack all the registers which are used in the loop 2. Now when you're popping, I have to pop this first, and later this, and lastly this. The popping operation should be done in the reverse order of the push operation. We are popping the loop 2 registers, and then we are popping the loop 1 registers, and finally we are popping and restoring the registers R4 to R11. So next, there are two more assembler directives, one with the name map and another with the name field. So these two can be used to define and allocate the space for the variables and arrays on the processor stack. Now how to do that? Like this: map 0. This says what is the starting address from 0, and then a field 4. So a is a variable now which can store a 4 byte of integer at offset 0, and b is another variable which can store a 2 byte integer at an offset 4, because this is saying that the starting address is 0. Since it's a 4 byte integer, so this a is going to occupy the 4 bytes and 0 to 3, and this will occupy from 4. The offset is 4. And similarly c is another field, 2 byte integer. This offset is 6. This is 4. Now 5 and 6 are reserved for this. 4 and 5 are reserved for this B. 6 and 7 are reserved for C. And next, D field 64, you can say offset is 8, because 6 and 7 are reserved for this. Now next, from 8 it will start and it will go up to 64 bytes. And length field, again I'm initializing it to 0. I'm saying it's a 0 length. It basically used for storing the length. Making the most of the available registers. Now you understood many tricks, Karana. When you want to use more than 14 registers, what are all the things you can do? You can optimize your code and you can try to reduce the usage of registers. Another thing is, if you don't have any option, you want to use more than 14 registers, then you have one option, that is saving onto the stack. There is another technique also which you can use in order to make use of the registers efficiently if you need more registers. So there are several tricks which you can use to fit a several 32 sub 32-bit length variable in a single 32-bit register. That means one single register you can go for storing two values. So a sub 32-bit. Say for example, I have a variable of 16 bit and another variable of 16 bit. Now this two 16-bit variables can be stored in one 32-bit register, and this also increases the performance and also reduces the code length. Now here we have the example for the same. See, this is what I want to do now. So table of index, I need to assign it to the sample, and the index I need to increment like this. Index is equal to index plus increment. Let us assume index is a 16-bit number and increment is again one more 16-bit value. Now we can pack this index and increment in a 32-bit value like this. Now this upper 16-bit is index and the lower 16-bit is increment. So when I want to finally compute the new index value, this is what I do. Now this index value, which is here in the most significant 16 bits, I take it to the least significant 16 bit by performing 16-bit right shift, and then I add that with this increment. Now when I'm adding this with increment, I have to mask this. I have to mark this part 0. Now this you have to take here. When I take this here by performing the right shift, index comes here and this is all 0. Say for example, index is 5. When I shift here, index is 5 and this is 4. It is 54 actually. Now this index, to take the value 5, this index should be shifted here. Now to shift this, by index left shifted by 16 times. Now it comes here. Now 5 comes here and this is 0. 0, 5 it is. Now this is 0, 5 plus. Now the original value here is 5, 4. I don't want this 5 now. What is that I have to do? I have to mask this. This is masked, made as 0, and this is 4. Now 0, 4. Mask MSB increment 0, 4. This is 0, 5 plus 0, 4. How much it is? 9. And that goes to this. And the same assembly language implementation is shown here. Now if there are 16-bit values, two 16-bit values to deal with, then these two 16-bit values can be packed in a single 32-bit register like this. Now you are reducing the code length, and at the same time the performance is also increased. Now, there's another example, SIMD. There is something called as single issue multiple data architecture. One single instruction dealing with multiple data items at a time. Now, for this, we are considering the example of multiply 8-bit pixel. Process 8-bit pixels in an image using add and multiply instruction to achieve some SIMD operation. Now, my intention is to merge two images. Say, for example, I have two images, two pictures, X, and another picture is Y. I need to merge them and produce a new image, Z. Now, in order to merge them and produce a new image, I got to deal with the 8-bit pixel. So, if it is a grayscale image, the pixel, each pixel is 8-bit pixel. That means the intensity value can vary from, when I say 8-bit, it is 2 raised to 8. It varies from 0 to 255. 0 to 255. The intensity values vary from 0 to 255. Now, I say let xn, yn, and zn denote nth 8-bit pixel in these images respectively. Now see, now I have all the 4 pixels. So this is 1 byte, this is another byte, this is one more, and this is totally. So these 4 bytes are representing 4 pixels. Now I have 4 pixels stored in one register. And similarly I have here 2 stored in 1 byte, one word. This is one word, totally 32 bits. So this is what you can do. So that means now by storing 4 bytes in this is 1 pixel, another pixel, third pixel, fourth. 4 pixels I'm handling simultaneously by using one register. So this is another example. Okay. So summary now of register allocation. So ARM has 14 available register for holding the general purpose data, R0 to R12 and R14. So R13 and R15 cannot be used. Now need more than the 14 local variables, then you have to use stack, store it onto the stack, and you have to use the register names instead of the physical register numbers, because you understood already the benefits of using the register name instead of the physical numbers. But there are few cases where you have to use the register number itself. So that is when you're passing the arguments, and when you're performing the load multiple and store multiple operations, and when you're performing load double and store double, and store multiple values in the same register. That is what we discussed in the previous example. That is index and the increment value. Index is a 16-bit number, increment is a 16-bit number. We stored these two inside one single register, and store multiple pixels in one register again. That is what we stored 4 pixels in one register. So this is the summary of the register allocation, and the next topic is conditional execution. So this we have already understood in the previous classes. That means every instruction in ARM can be conditionally executed. That means you can embed a condition as a part of them. And embedding the condition as a part of the register, as a part of the instruction, also improves the efficiency of the code and also reduces the code size. Now here is the example. The following C code converts an unsigned integer 0 to 15 to an hexadecimal character C. Now this is what I'm doing now. So a simple if else high level statement, and the equivalent in the C code which is embedded with the conditions I can show you. If I less than 10, this is what I'm doing. C is equal to, say for example, I value is 0. 0 is less than 10 true. 0 plus 0 written in single quote. So when you write something inside the single quote, it will take the ASCII value. Now the ASCII value of 0 is 48. 48 plus 0, and the character is 48. ASCII value, it's hexadecimal. 48 is the ASCII value. ASCII value of 48 is 30. C will be 30. Else, if it is not less than 10, say for example, if it is 10 less than 10 false it is, it comes here. And that time what we are doing, so we are subtracting 10 from the ASCII value of uppercase A. ASCII value of uppercase A is 65. If I convert this into hexadecimal, it is 41. 41 minus 10 is 31. 31 plus I is 10. It is 41. 41. So that is nothing but 41 is A. So 10 I have given. 10 less than 10 false. It comes here. 65 minus 10 or instead of 65, let me convert it into x of 41 minus 10, it is 31. 31 plus this is 10, I value is 10. It is 31 plus 10, 41. 41 is nothing but A, uppercase A. Now, and the equivalent hexadecimal is like this. Now, I am comparing I with 10. Now, as long as it is lower, I add hexadecimal ASCII value of 0 to I, and that is the character. Now if it is IR are same, so this is what I'm doing. This is what I'm, same logic. Now I can execute and show you this. Here is the program. So this program will execute. Save, compile, build, debug. Okay. Absent now.